All right. Okay, so we're going to talk about logic and proofs. And so this is chapter 4 in the textbook. And so we're going to start off with the thing we learned of tautology. And this provides our bridge to the stuff we're going to talk about now. So we learned about tautology and absurdity. So tautology is if we have some truth table and we get to something that's all true, then that's a tautology. But if we have something that's all false, then that's an absurdity. Absurdity, right? And so a tautology gives us something that we can say is logically equivalent. Which is useful when if we have something in one form and we know that it's logically equivalent to something in another form, that's kind of what will help us as we go forward and prove things. So for example, we know that a squared minus b squared is going to be logically equivalent to the expression a minus b times a plus b. For any real number, right? We know that that's going to be the case. These two expressions, so this expression and this expression, they're logically equivalent. And so we can go between one and the other and know that it's going to give us the same information. So it's going to, if we have a value for A and B over here, the truth value for that, the other side is also going to hold. And so this leads us to these. So we're going to have a theorem, which is a bunch of additional laws for propositions. So this is theorem 4.1 in the book. And this has our favorite things like commutative laws, which gives us something like P or Q is logically equivalent to Q or P, which feels a bit duh, but is true because and to prove that we can write a truth table, right? So we can have P and Q. And then we can say P or Q and compute that. We can compute Q or P. And we'll get both of these, like we'll get the same exact answers for each one. And so then we say that they are equivalent. And this also holds for P and Q is equivalent to Q and P. And then we've also got the associative. The fun stuff like if we have P or Q or R, that's equivalent to, we can move around the parentheses and say P or parentheses Q or R. And this also holds for and. We've got the distributive laws, which is where we have P or Q and R. That's equivalent to Nope, sorry, I'm looking at the wrong line. P or Q and R. P and R. Or Q and R. And see, so this and R kind of gets distributed to each one. And so having R over here means that we can distribute and say P and R or Q and R. So we can distribute that through. We can double negate something. And so this says if we double negate P, that's just equivalent to P, right? So two knots make a no knot? I don't know. All right, so that's the double negation. And then we get into De Morgan's laws. Which we've talked about with set notation. And so that is if we negate P and Q, that's equivalent to negating P, and then we flip this operator and then negate Q. Or if we have P or Q, that's equivalent to not P, and then we flip that operator, and then we negate Q as well. Then we've got the idempotent laws, which are if we have P or P, that's equivalent to just writing P, and the same for and. So if we write P and P, we can just simplify that and just write P itself. And so the example the book's got for De Morgan's is, let's say, so it's going to be hot later today. So if my friend goes and asks, are you hot and tired? And I say no, then I'm neither hot nor am I tired, right? If I go and I ask, and someone asks, would you like tea or coffee? And I say no, then you could reasonably assume that I would like neither tea nor coffee. If you go to a barbecue and do you want burgers or brats? You want neither of them, right? So we can also verify these with truth tables. So let's build the truth table for which one do they have? So they've got this one. So we're gonna do the truth table for this. And so again, we start easy. So we'll start with P and Q. And then we'll build up. So we can have P or Q. And this is true, 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 and false. And so we've got the inside part of that. And then if we negate it, so then not P or Q is just this column flipped. So false, 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 true. And then we look at so we've got the left-hand side all sorted out. So now for the right-hand side, so we already have P, we already have Q individually, and so we look at them negated. So not P and not Q. And so not P is just this column flipped. So that's false, false, true, true. And not Q is similar, which ends up being false, true, false, true. So we've got that. And then now, since we've got both components of this, we just AND them together. And so not P and not Q gives us false and false, which is false. False and true is also false. True and false is false. True and true is true. And so then, okay, let me abbreviate that A and that B. And then all we have to do is see, are they equivalent? And so it's been a weekend, so let's go back to the equivalence tables. All right, let me find what page those are on. That's implication. Okay, this is on page 42. That's 57, 46. 43, 42. Okay, and so this gives us our definition for how do we define this biconditional. So if both of them are true, if P and Q are true, then the biconditional is true. If one of them are false, then it's false. If both of them are false, then it's true. So let's see how that applies. So let's see. This is A. This is B. All right, so in this line, both of them are false. So this is true. In the next line, both of them are false. So the biconditional is true. In the following, again, they're both false. And then in the last, they're both true. And so with that, we get a tautology. And so that tells us that saying that A, if and only if, this biconditional, B, now we can say they're equivalent because we've shown in our truth table that there's a tautology. And so this is kind of how, this is one way to prove these kinds of statements, where we draw a truth table and say, here's all the possibilities, here's all the ways this could go. And we prove in this column that it's all true. Therefore, the statement A will always be equivalent to the statement B. Okay. Any questions on that? Great. All right, so there's also this notion of what we call a contrapositive. Which is essentially saying that if we have P implies Q, this is going to be equivalent to not Q implies not P. This is the contrapositive. And so what is this saying? Basically, it means we've got some sentence P implies Q. And so we assume that the conclusion, we negate the conclusion, and that implies that the hypothesis is false. So the example that the book's got is, so if Joel is drinking alcohol legally, then Joel is at least 21 years old, right? So this is our proposition. And so we've got, let me highlight this. So this is P. So Joel is drinking alcohol legally. And then this is Q, that Joel is at least 21. And so the contrapositive of this is if Joel is not 21, Joel is not at least 21, then Joel is not drinking alcohol legally, right? Right. And so the negation of this statement, the negation of P, so if he's drinking alcohol legally, the negation it could be that like he's drinking it illegally, or it could be that he's not drinking it, right? So either of those could be true. And so this is kind of where with natural language, um, we have to kind of be super specific. But with mathematical language, it's slightly easier. And so let's see. Okay, so we don't have examples with mathematical language yet. But I would like you to turn to your neighbor and do let's see, number 4 on page 70. So let me scroll over to page 70. 71. Okay, which is this guy. So taxes are complicated. And so let's break this down into statements. So this has more than just P and Q. I think it's got 1, 2, 3, 4, 5 propositions. And so first write it in terms of proposition letters, variables, and then find the contrapositive. So find it in terms of P, Q, R, S, T, I think. And then find that equation and then negate it. Sound okay? All right, go for it. So what's P? And then Q is filing jointly. R is your income's less than 100,000. And then S is claim no dependents. And then T is you are eligible. $10.40 Z. All right, so what's your, someone read me there. So let's say A is my my hypothesis. What's the equation in terms of PQRST? Call it out. Right. And so, yeah, so we could, so we can, we could do that if we wanted to. Again, we just talked about associative laws, so maybe, so I don't think, so if you don't have these, I don't think it's wrong. If you do have these, I also don't think it's wrong. Again, we talked about those laws, and so we can like verify that it's equivalent. And so I think obviously B is just our statement T that we're eligible to use this form. And so the contrapositive is, so if we have A implies B, then the contrapositive is not B implies not A. And so then we get not T implies, didn't get it yet. So I'll do not P or Q and R and S. This bug is relentless. And so then to distribute this, De Morgan's laws say this is not P or Q, and we flip it. And then we can distribute this. If we don't have parentheses, we could distribute it with not R or not S. If we did have parentheses, and R and S, then it would be, so we would have this, but we would have instead, so we would flip it, and then this would be not R and S, and we haven't done that distribution yet. And so this gives us not P and not Q. And then if we were to do this distribution, we would get, we'd have not R or not S, right? So if we have it in parentheses, that does get us there. If we don't have it in parentheses, we can just distribute it one step sooner. Did anybody get anything drastically different? Great. Okay, so some words. So let's say we have something in the form of P and Q. This is what we call an implication. If we've got something in the form of not Q implies not P, this is, as we just discussed, the contrapositive. We can say if we have P equals, P implies Q, and then we just swap them, where we have Q implies P, This is the converse. And then there's one more, which is we've got P implies Q. And so if we just negate P, we negate Q. This is what we call the inverse. And so in terms of equivalency, there's only two in here that are logically equivalent. And they are the implication and the contrapositive. And so we can show this using a truth table that these two are logically equivalent. The rest are just useful terms to know. So if we have some sentence in the form of P implies Q, then it's useful to know that like, oh, the converse is when you just swap them around, or the inverse is when you negate each one. But the inverse is not logically equivalent to the implication. Only the implication and the contrapositive are logically equivalent. So only those guys are logically equivalent. The rest are just useful terms to know.
Something like converse occurred.
So let's see. So the book's got so P is quadrilateral, Q is a rectangle. And then the statement Q is that the quadrilateral Q, capital Q, has two pairs of parallel sides. Right? And so the implication is if a quadrilateral is a rectangle, then it will have two pairs of parallel sides. The contrapositive is if it does not have two pairs of parallel sides, then it is not a rectangle. The converse is if it has two pairs of parallel sides, then it is a rectangle. So can we think of something that has two pairs of parallel sides that is not a rectangle? Yeah. Well, because a rectangle like is defined by two parallel sides, but also has right angles. And so the converse gives us a parallelogram, which is not a rectangle. And so they're not logically equivalent. The inverse is if a quadrilateral is not a rectangle, then it does not have two pairs of parallel sides. So if it is not a rectangle, so it could be, I don't know, a trapezoid, then it does not have two pairs of parallel sides, which that's true. So it doesn't mean that they're not, the statements, the implications can't be true. It just means that they're not logically equivalent. And so when we go into proofs, if we're trying to prove the implication, sometimes it's easier to look at the contrapositive and prove that instead. All right. The book's got a truth table for the contrapositive. So, if you are curious, I leave verifying this to the reader. And let's talk about predicates. So this one is, I don't know. This section is not my favorite, but it's important. It introduces important information. And so we've seen things before where something um, like x is an integer and 5x is equal to 20, or like you can say x is your grade in Math 240, which is for this one, like that's fine. It's not specific, and so we can't say that it's a proposition. We need more information. And so for the things that we've needed more information for, these are now called predicates. The book also says propositional form or open sentence. And so let's say we've got something like x squared is greater than x and x is less than 10. So each of these is a predicate where we can say x squared is greater than x. That's fine. It's like a mathematical expression, but I need more information to say whether or not it's true. So that makes it a predicate. This is the same, where x less than 10 is an expression, but I need some information about x to say whether or not that's true. And so this example has us go through, let's find the set of values that make this true. So for x less than 10, so again, we are assuming that these are all going to be integers. And so what set of numbers is going to make x less than 10 have a truth value of true? Right? Yeah, anything less than 10. So if we use interval notation, do you guys know interval notation? Yeah, great. Where do you learn that? Pre-calc? Great. Yeah, which is why I ask. Okay, so that makes that true. What about for x squared to be greater than x? Under what conditions is that true? X is not equal to 0. X is greater than 1 or x is less than -1. So yeah. Okay, so 0 squared is not greater than 0. So 0 is disallowed. 1 squared is not greater than 1. 2 squared is greater than 2. 3 squared is greater than 3, and so on. -1 squared is greater than -1. -2 squared is 4. That's greater than -2. And so going down, so going up and going down, it's going to be okay. So for this, we can say, so negative infinity to -1 union 2 to infinity.
X is less than 10. Did it go all the way up to 9 to 10?
Um, So let's take, so x equals 9. It's less than 10, so that's good. X equals 10. Is that less than 10? And so we could either say comma 9 square bracket, or we could say comma 10 open bracket, like the parentheses. Since we're dealing with integers, these two are logically equivalent. Okay. So the book. All right, so okay. So the book has a nice tidy equation. Let's try and get there. So we've got two sets. And we want to find the set of numbers, the set of integers under the conditions where both of these are true. So it's like, so now we want to find like the intersection of this set and that set. So what's that intersection? So let's color the right hand one green and the left hand one blue. So for the green one, let's say this is 10 and that's 9. So for the green one, anything below 9 is fair game. For the blue one, that should be a square. That should be a square bracket because -1 works. So anything under -1 and anything greater than 2. There's also numbers between 2 and 9. Wait, so is the book wrong then? I think the book might be wrong. Okay, so once we have this, then we see that the overlap is up to -1. So negative, and that's an 8. Negative infinity to -1. And 2 up until 10. Oh, nope, the book's not wrong. It just wrote it a different way. And so the book wrote negative infinity to 0, union 1 through 10. Can we see how those are the same thing? Right? So we said we stop at -1, but really we want to stop before 0. So that's okay. And then we want to start at 2, but we can start after 1. And so two ways of expressing the same things when we're working with integers. Questions? Okay, so I want to tell you about the quantifiers because you'll see these going forward. There's a bunch of examples in the book that you'll probably play with in the homework, but so let's see. Let's talk about the sentence. For each real number Man, handwriting is not here today. For each real number x, 3x minus x squared is greater than 0. This happens to be false, but let's not worry about that for a second. We're gonna talk about how we express this in symbols. And so there's quantifiers that help us like say some specific words in these kinds of sentences, and we say it in symbols. And so we've got that sort of sentence. We also have there exists X in the set A, B, C, D, and F such that your grade in Math 240 is X. And so the things that we're going to quantify, we're going to say for each real number X, or there exists an X. So we're putting some quantifier on X, right? There's a variable in these sentences, and we're quantifying it in a different way. So one of them, so for each, we're saying for any possible value, then this statement is true. Or there is one grade in this set that will be your grade, right? So either there's multiple options or there's one option. And so we say that, so there's, the book calls them universal and existential quantifiers. But this is basically saying like for each or for every or for all or for any, etc. You get the idea. We're saying like this is a universal quantifier. So for any value that this could hold, and we write that as the upside down A. Let's pull up Detectify really quick and see how we type that. I think it's for all. It is for all. And so in LaTeX, this is / for all in math mode. And then the existential, we write with this backwards E, and we say something like there exists. Just saying something exists and there is at least one. And if we want to say that there exists exactly one, or at most one, then we say it with a little exclamation point after it. So the backwards E is there exists. And so to say for each real number X, we can say it instead as, so for each number X in the real numbers, and then we can have this equation. And that's how we write it in symbols. And so for this one, we can say there exists some grade X in the set A through F. I know E is not included, but in the interest of time. Such that X is your grade in Math 240. Right? So this is just our way of how do we write something in symbols? And so you'll see this going forward. So essentially, the upside down A is for each, for all, for any. The backwards E is there exists. Let's see what the command for the backwards E is. I think it's there exists. No, it's just exists. Say that again?
For there exists only one, just put an exclamation like that.
Yeah. I don't think that's a dedicated. Yeah. So because exclamation point is a character you can type on your keyboard. So let's try that. BBR. And then we can say exists X in the set A, B, C, D, F. And that gives us that. The indentation here is weird because that's something like after a section, after you start a new section, it won't indent that line. And then for each following paragraph, it will indent. So if I wanted this to not indent, I would say no indent. And then that moves them back onto the same line. Okay, so I think that's it for today. Next time we'll skip 4.3. We'll talk about how to construct a logical proof on Wednesday. Homework 4, is to write the solutions to homework 3 in LaTeX. And I've been racking my brain on how you should do that when I have your homework 3. So I'm gonna make it instead to write the instructions to homework 3 in LaTeX because you have access to those. So you've got the instructions in the book, so just typeset those instructions in LaTeX. And I'll change the Canvas assignment to do that too. Thank you. I will see you on Wednesday.